Hi everyone, I'm Jeremy Harper, and today we're going to be talking about large language models. This is the first in a series of practice runs that I'm doing for the 3.5 hour lecture I'm doing at the AMIA Summit. So there may be a few um, rough patches along the way. Bear with me. We're going to get there, and we're going to have a lot of fun. So this session is split up into a number of different parts. The important thing is today we're going to be trying to do an introduction of LLMs and their impact on healthcare. And we're going to then talk in a future video about data management, some ethical considerations. We'll look a little bit about how we can do group activities, practical applications, some hands-on demonstration, although I'm kind of interweaving those all along the way. And just some potential group projects that we can all do as a group. So when we think about mastering LLMs in healthcare informatics, we're looking at where the foundation of LLMs are, and we're just going to build on that with where we're getting the data, how we're getting the data, where we're making decisions. Then we move on to building into practical applications of how we're using all of these tools. We're leveraging future trends and then collaborative projects. And just as a little extra, for anyone wondering, all of these slides have been made uh, through that previous video that I did, where we talked through how I'm going to prep for a 3.5 hour lecture, and I leveraged the book that I've written on healthcare and large language models, and built out slide decks. And then I took those slide decks, did a little tweaking, and pushed those over into something called napkin.ai, which does some very pretty visuals. And I hope you all like them. So, why do large language models matter in healthcare? We've been using AI in healthcare since I started in the industry 20 years ago. But our ability to use AI has been changing over time. In large part, it's because we now have more compute cycles than we've ever had in the past. Compared to when I started, uh, I did a calculation for my book. My current iPhone has as much power as a 1997 supercomputer. I started in the industries in 2006. Probably in about 6 years, we're going to have the same number of flops in an iPhone as roughly when what the supercomputers could deliver. That gives us some phenomenal opportunity to do some really amazing things with technology that we are essentially brute forcing. So I have lived through where our AIs could only be in the kilobyte size. I have lived through where they can only be in the megabyte size. And now, because large language models are so ubiquitous and flexible, we're getting to where we can apply AI that is in the gigabyte size. And that brings up some really amazing opportunities. It gives us the ability to just absolutely transform our clinical operations. Every step of the way, we have opportunities to start applying and start leveraging something that can not replace a human, but can assist a human. As a clinician, communicating with patients can take up a fair amount of time. Having the ability to have notes pre-generated, having the ability to have notes summarized if they are longer notes, having the ability to review and ensure that I'm taking all of the actions that are advisable, uh, being able to go in and have all of the processes and workflows that surround my clinical activities be improved upon and flow more seamlessly, all adds to the clinical care journey for a patient. They also can do so much in terms of communication bridging. If English isn't your first language and you need some communication bridging, large language models give us the ability to do many of those communication activities where specialists had to be employed in the past. And it's not that we want to eliminate the specialists. It's not that we want to um, provide a lower capability than what the specialists offer. Frankly, the specialists are typically the gold standard. But if you've worked in the industry long enough, you've heard the stories of when specialists were unable to deliver, um, and when they failed people. And so having a backstop of something that's generally pretty good is amazing. Having a tool that can be leveraged for real time translation can be very powerful if you can't get a hold of anyone. And that does occur sometimes in healthcare. So all of this comes together to give us the opportunity to just enhance healthcare delivery. And that's exciting. So, one of the things that I want to highlight for you is we have been on a journey towards large language models for 50 years, 70 years. I'm going to show you some examples from the 1950s when perceptrons were first invented. Um, we have a lot of different pieces and parts to the puzzle and how we've been evolving language models. When I first entered the industry, most of our language models, where we were interacting with free text, consisted of us doing string matches and fuzzy matches. Then we started adding role based natural language processing. Then we started going and we started adding general transformers. So 2016, 2017, I believe the big Google paper on the attention mechanisms and all you need is attention was released, which absolutely pushed the state of the art in a new direction. Before that paper was released, I was participating in and helping design a number of different research studies in a number of different technologies and capabilities where many of those have gone to the wayside over the last 6 to 8 years. It is likely that many of those same techniques will be reintroduced as we find opportunity for them. Uh, at the end of the day, they all had something going for them, but they were not as powerful as the transformer attention mechanism. That transformer attention mechanism is still being explored, still growing. Every now and then on the state of the art side, I see people trying to reapply some of these other techniques that we were using back then. But then something about transformers gets released, it advances so far ahead of uh, these other techniques that it becomes hard. And so, most likely, it appears that we're going to explore the transformer space in its entirety before we start um, kludging on some other techniques. So, after the attention mechanism came out, we saw some practical implementations like the GPT-1, the GPT-2. We're going to be looking at GPT-2, which was released by OpenAI back when they actually were open source. The BERT models, and so I want to say GPT-2 was released in 2020, uh, and I was running it on Google Colab. I've got a project where I want to go into Google Colab with all of us and look at GPT-2, and that will be a future video. While GPT-1 was released, GPT-2 was the first time that we started to see true glimmers of universal use. It was able to go in and continue a paragraph and build an entirely new paragraph. Many of the earlier models struggled to build much. Um, and one of the things that made ChatGPT so interesting was its ability to actually have a conversation and better output what people were looking for. Whereas these earlier models with like GPT-2, it struggled to output what you were hoping for, what you were looking for. It was instead just looking to do a continuation of the text that you currently were typing. So before we jump into all of that, there are a few core concepts of terminology that I want you to have been aware of. There's the token. So when humans talk, we do it in words. Uh, Supercalifragilisticexpialidocious would be a single word, uh, popularized by Mary Poppins. Um, a token is how a large language model thinks. It is not a word. It is a part of a word, typically. Every now and then it can be a whole word. The computer system, the math behind everything, makes the determinations, how it tokenizes everything. And sometimes it tokenizes in a very uh, intuitive manner. And sometimes it tokenizes in a way that humans would never tokenize. We'll look at that in a little bit more detail, but in general, the easiest way to think of large language models is that a token is the equivalent of a word. There are transformer architectures. Transformers are what allow us to leverage the attention mechanism. It is layers upon layers of perceptrons, and we're going to explore exactly what perceptron is. There's a context window. So a context window is how much text that I can put into the large language model for it to be able to reference to be able to push out the other side. It's the amount of text that's actually visible to the model. Early models had very small context windows. The latest open source Llama models have 128,000 token context windows. And Google has models that are 2 million token context windows. We'll explore a little bit more about what context windows actually mean, but the important thing to remember is that context windows don't mean that it's going to be reacting to the entirety of the text when it's generating, but it is able to reference anything within that text. So that's how retrieval augmented generation RAG is used, where it goes and grabs a bunch of relevant text, slaps it in to the prompt invisibly in the background, allowing the language model to reference things that it might not have been trained on. Inference is an important term. It just means that, hey, during the inference process, we're actually generating the data. It's referring to when we do all of the math in the background of the system. So I just thought this was a nice way to bring it back to healthcare. We're going to be talking more about how large language models work, but when we're thinking about AI in healthcare, we want to think about how we can actually go out and do something. So maybe we want to do clinician support and task automation. That is looking for opportunities to automate repetitive tasks. If we're doing clinician support and decision support, we want to look for opportunities that are mainly where do people make decisions and how can we help assist that decision, either by giving them recommendations, making the decision for them. Task automation and patient interaction is also a really valuable opportunity. So we can make patient-powered chatbots where we can give them strong, clinically relevant backgrounds and information. We can collect extra information from them, chatting with them to get better understandings of their symptoms. We can also go in and we can look at how do patient interactions and decision support impact clinician burnout. So that's our healthcare piece. Right now, we're going to think about how do large language models actually think. And at the end of the day, they are a fabulous, amazing next word prediction. Um, they don't understand like we do. And we're going to get a very strong understanding of how they think. My strong opinion is large language models will never cross the artificial general intelligence barrier. That doesn't mean that they aren't fabulous tools, that there are a lot of things that I would have said uh, might require general intelligence many years ago that it can accomplish. Um, but in many cases, it's not actually thinking. One of my fun side hobbies is to write fiction novels. And I have trouble focusing long enough to actually write a full book. I really like world building and will often get bored in many of the minutia that is actually required to tell a good story. I will be very focused on world building. So I will define my story. I will define my world. I will define how my characters interact. I will go have 8,000 word prompts and I will feed in prompt one for this is what I want to happen in the chapter. Prompt two, this is what I want to happen in chapter two. The smartest models go off the rails after you've generated multiple pages of text. They will forget things. O1 Pro, which I have access to, is still one of the smartest models to handle all of this when you're going into. So it's not as good as Claude when you are doing baby prompts that are not 7,000 word prompts, but it's better than any other that I've tested when you are going to do ridiculously large prompts. Um, so when I built the sci-fi book that I never released, which had them on the moon, and they get to the moon, and they're out in space. They do not have artificial gravity, and uh, the system flips between having gravity and not having gravity, not with any logic. Um, it doesn't remember, it doesn't understand the physics of the world. It also had where it parked a alien spaceship on the moon, but then they were traveling to a spot in space, and it completely forgot where it had put the alien spaceship in the difference of about 2 pages worth of text. These aren't intelligent as we understand it. They are fabulously intelligent in ways that we don't understand. I actually have an example I was going to show you of where they are fabulously intelligent in ways that uh, are different than us. So there was a new tool released called Zonos, and so all I wanted to do um, was some people had released it so it can run on Windows. It's using PowerShell. I ran it. I really like it. I don't want to run it on PowerShell, and so I told it, "Here is all of the code." And I had a tool that grabbed everything from GitHub and put in all of the programming code. And I said, I want to run it in Anaconda. And it comes back and it gives me step by step instructions and any and all code required to be able to do it, which is really a small amount of modification. I did the same thing where they didn't release an API and I wanted to build an API and none of the existing APIs were what I wanted. And so I literally just said, here's the API, here are the endpoints that I want. And it generated and delivered that. With It's broken, but it's easily to fix broken. Um, and that's a type of intelligence that I would have never attributed to a next word predictor. So, what do I mean by next word predictor? Every word has many different branches where it could be going. I could just feed you the word I, and you might think, pledge, I pledge, or I guess, might be coming out of my mouth next, or 10 million different things after I. So if I go, I pledge allegiance, you're going to be thinking that I might be starting, I pledge allegiance to the flag. Uh, or maybe I'm pledging allegiance to 4-H, or I'm pledging for allegiance, or I pledge to deliver on this 3.5 hour lecture that I promised to a long time ago. Um, think of it all as branching logic, incredibly complicated, amazing branching logic. So I ran this in GPT-4 217, so just recently. I tried it in the others. I liked the GPT-4 because it was just simpler. O1 and O1 Pro just put too much text. And so, uh, and ChatGPT gave me the easy ability to write Pledge Allegiance. It sounds like you're starting the Pledge of Allegiance. Here's the rest. I pledge allegiance to the flag of the United States of America and to the Republic. I pledge allegiance. It sounds like you might be starting the Pledge of Allegiance. So these are almost the same. It sounds like in both of these. And then it became you instead of your. And then because it's you, it became might instead of starting. And to the flag of the United States of America and to the Republic. So all of this is the exact same in these two. But that's the pledge. That's the Pledge of Allegiance. Both of those are very reasonable responses, but we inject randomness into large language models with what's called the seed, but it's just a random number, which will bias it to make other selections. So if I have a seed of 10,000, maybe I go with allegiance. But if I have a seed of 1 million, maybe I go with I pledge 2. All of the text in a large language model is converted to numbers, and hey, there's a lot of different layers. And so we take all of those numbers, we get a new number out, which we give a specific numeric representation for how likely it is, and then we do a randomizer that selects the next word. So we enter the prompt text, we split it into tokens, we convert those tokens to numbers in a multi-layer space. We go take it into the large language models. These days, it iteratively refines it. It gets eventually to where it predicts the next most likely token, and it outputs that token, and then it goes into a great virtuous cycle. Um, and there are some things that we can do that make it very easy to continue outputting the next token after we've started until it finishes, and then you can enter another prompt. We're not going to do this today, but this is a future one where we're going to pull up ChatGPT 2. I want to do that one specifically in a different video. And we're going to look at what happens on Google Colab with ChatGPT 2, or I'm sorry, GPT 2, which was released by OpenAI, which is the same, it's a previous generation to ChatGPT, essentially. Um, and if I give it the phrase, please predict whether I have pneumonia from the following list of symptoms: chills, cough, shortness of breath, fatigue, muscle aches, headache, loss of taste, and sore throat congestion. And we're going to look at exactly what it outputs. So there are a lot of ways that you can learn a lot about the underlying math. I'm not going to be teaching you the underlying math in any of these videos. People who are better educators than I am have accomplished that. If you want to understand the math in an intuitive, useful way, go to 3 Blue 1 Brown. They've got a YouTube channel. They've got a video called Transformers, and it's now a series of different videos, and it is absolutely fantastic. If you are a hands-on person and you want to understand how these GPTs work, uh, someone last year went and converted GPT-2, which is a very reasonable large language model, into Excel. And you can literally track how it all works in Excel. This is a 1 billion, I'm sorry, a 1 gigabyte binary file, which I've had running on my Windows machine uh, on many occasions. I'm still trying to figure out how we can get it to be performant enough that we can do something with it in the classroom. But it's kind of fun and interesting. And most likely, I'll produce a video just showing it off because it's kind of fun. Ars Technica also links to videos, which other people already did with it. Um, again, words are converted into tokens, which are converted into vectors, which are just numbers. And it's all put into a vector space because it's AI and we have 10,000 layers. All of this is going to be fun for the math nerds. I understand most of us aren't math nerds, and so I happened to run across something. It's a YouTube video, and I'm going to give you the channel next, which is just intuitive and it's hands-on, and I loved it. And I'd really encourage you. I've watched this with my nephews who are 11 and 9. I watched this with my daughter who's 8, and it takes some explanations for them, but it's a really useful way of grasping uh, in a very hands-on, tactic, practical way how these things work. So what they did is they did a bunch of different switches. Those switches are realized here. And so we want to train a perceptron to always say whether we are showing a T shape or not. So it's a yes or a no. And you have different dials that you can adjust. And if it is in the positive, it's a yes. And if it's in the negative, it's a no. A perceptron is an algorithm. And literally all we're doing is if we have a positive T, we take every aspect of that T shape and click it up by one notch. Everything that's not a T, we click down. And as the T progresses in a 4x4 grid, a T can only take shape in two places. And then they show a J example, but it'll work for any example that you train in. Um, well, most examples that you train in. uh, you just keep cycling through your different use cases, and as long as you're moving the positive use cases up and the negative use cases down, it will eventually result where it can do prediction. And they have some really, really intuitive, useful pieces of this video that I'm not going to go into, that I just really encourage you to take the time, watch the 15 minutes, if this is something that you're interested in. So, being that we're really interested in large language models, I wanted to give you something hands-on that you could do that would help you intuit this. And so I'm going to show you an example of where I am getting an output from the system that is my process. I didn't try and prompt engineer. I knew that this was a single shot. Hey, I just need this to build this thing one time. And so what I did was I took the screenshots that I showed you there on the PowerPoint, and I told it I found a video where someone made a physical representation of a perceptron. I want you to program a game where a user could click the dials and have the same experience to learn about perceptrons. And then I copied their entire transcript. The system goes and builds me something. It built it in HTML. Wonderful. I did not tell it anything about the HTML. And so this is what it came up with. It's wonderful. It's lovely. I've got input targets. I've got other targets. I have weights and outputs. Well, that doesn't look very much like what I actually wanted. So I went back to it and I said, here, let's do this. Um, we don't have a visualization. I want a visualization like in the image. Not too bad. You gave me a visualization. That's wonderful. Well, that's still not very intuitive. So I gave it a little bit better. I said, that's better, thank you, but we need to do the following. We need the grids where the model's being trained, and I'm going to just start specifying I need 4 different grids. The second 4x4 grid needs to be modifying the weights and balances. So what we're doing is we're trying to just replicate that original image that we were looking at. Um, and the third outbox where we're saying the total calculated, and this is what it generated. And it's starting to look better. But whenever I click the train step, it's already corrected the training pattern. No update needed. So it turns out that if I go make some modifications, it starts working. Um, I, I was a bit torn, but I decided that letting the person know that they've hit the maximum training steps for getting a classification was kind of useful. It keeps you from going and clicking through. But there were a few things that I still wanted to change. All of this was with me doing no real coding. And eventually I wound up with this where, hey, look, I get some signs, I get some better learning labels. It works the way I actually expected it to. And so in the class, I'll just share this HTML. Uh, I'd encourage you to just go have it build the system yourself, get some practice with it. I do not currently have a GitHub for this type of thing. I'll probably build a GitHub and eventually link to it in a future video. So back to the PowerPoint. At the end of the day, this was an early example of how I was trying to explain this to people. And that perceptron is a much easier intuitive grasp. Um, in the multi-layer space, you remember that we mentioned these vector spaces? Um, every word gets assigned a lot of different vectors. It's the equivalent of all of these different dials that we're playing with. And so that's a level of math that you probably don't need to understand or want to understand. If you're also geeky about it, just chit chat with me. But the important thing for you to understand is this is how the machine is thinking. Everything is embedded in vector space. And so thinking as we currently define AGI uh, is very different. So there's a lot of marketing material going around saying we've achieved AGI, and they're lying. Um, did I say that out loud? So just be aware. So one of the things that I did want to just mention very briefly, because we're talking large language models, but I think that there's a lot of new technology. I was showing you Zonos a minute ago, and that's being able to take any voice pattern and replicate it, which is exciting for some of us. So diffusion. So this is the system where we get to type in text and have it generate an image for us. Something that I find terribly useful when I'm building presentations and going out and about. So one of the wonderful things about diffusion models is they're very intuitive and they're very easy to understand. So if I go and I tell it, I only want you to do a single step, it's going to generate an image like this. And if I tell it 5 steps, it's going to generate an image like this. 10 steps, suddenly you start thinking, I know what it's trying to generate. And at 15 steps, hey, that's starting to look like a person. At 150 steps, it looks like a much better person. Um, but suddenly this guy's arm's too long. It's really interesting how you can be in a hospital bed and it can go from this image to this image, where the gentleman is not only different ethnicities but also changing sides. Windows have changed sides. Um, how do large language model? I'm sorry. How do um, image diffusion work? Somewhat similar, actually, to large language models. But what we do is we train the AI in them so that we take an image and we make it fuzzier and we tell it to get back to that original image. And these are drastically stronger steps than what we'd be doing. But essentially, all we're doing is we're making images less good and telling the diffusion model to make the image better. And we keep doing that and we keep doing that until we get to a place where we can just give it complete randomness. And it will take that randomness and start building it towards whatever text description that we have provided it. Diffusion models have been applied to large language models. They've not taken over. Um, uh, but there are benefits to having good examples and making them a little worse, a little worse, a little worse, to help teach the system over how do we make it better. Again, you're all not going to be diving deeply into the math. unless in the classroom they want me to dive deeply into math. Just one of the ways that we measure things, and one of the ways that if you are in management looking at these things and wanting to understand your own internal team, what they're telling you, you have to get used to a what's called a rock curve. And it, when it's over the line, it's good. It's got a better true positive rate versus a false positive rate. And when it's under the line, it's bad. And just be aware that if you're building brand new, you should be generating things like this and you should be looking into it. So I've got one more slide that I'm going to do for this portion of the presentation. And then in the next video, we're going to be looking at key healthcare large language model use cases, real world examples. And so I, because we're going to be looking at GPT-2 in some detail, I'll pull this same slide up when we look at it on Google Colab. And just in case you don't know, Google Colab is a free resource and also has a paid model where you can get some temporary GPU usage, temporary processing power, and you can write scripts in Python and test them out. So it works out really well if you don't have those capabilities on a local desktop, for example. So maybe you don't have a GPU available. So with GPT-2, we do an input, we do the tokenization step. So we take all of those words, break them down into numbers. Uh, we go and we take that text and look at their positional embedding. So we break the text tokens into numbers. We do a multi-headed attention step where we're looking at the attention across many different layers. So those perceptrons, not only are they 40,000 perceptrons wide, there's a layer of perceptrons, a layer of perceptrons, a layer of perceptrons, a layer of perceptrons. And so we run multi-layers through. We go back and forth on this process 12 times. Eventually, we get to the language head, which helps us make the final determinations uh, and prediction values, and then it finally generates the output token. And all of this is really clearly laid out in that Excel spreadsheet. And so, with that, thank you for your attention. Those 42 minutes flew by faster than I ever imagined. And I hope that you have a great day.